So we've covered the features that influence acidity, and now that we understand a little bit about how we think about bases and using pKa value to measure the strength of a base, we're now going to look at those same features and see how they can influence the basicity of a functional group. First of all, let's remind ourselves of the equilibrium that we're interested in here. So we start off with our base, and we're going to add some form of proton. I'm just going to use protonated water for that in this case. And then we remember that this is in an equilibrium where the base will accept the proton to become positively charged, and we'll be left with water. So that's the equilibrium that we're interested in. But what we know is if we want to consider this in the form of a pKa value, the acidity, we actually almost need to consider the reverse reaction. So we think of the conjugate acid. So BH plus is the conjugate acid of the base, okay? And when you put some water with that, what we then end up with is the base and our acidified water again. And we have that equilibrium constant there, and because we're now looking at the conjugate acid, we can measure that using the pKa value. Okay, so just remember what we're looking at this time is the idea that the base is going to pick up a proton, and so for the base to be able to pick up that proton, it's going to need to have a lone pair of electrons or an unbonded pair of electrons that can be used in that process. So as we go through looking at those different factors, what we need to remember is it's often around how available is those electrons as to how easily it will be able to pick up the proton. But when we're talking about the pKa values, we're thinking about this process at the bottom where the conjugate acid, so BH plus, we need to think about how that is going to dissociate, that's going to lose the proton to act as an acid. And so something which is a strong base won't do that very readily. So therefore the pKa value for that will be very high, indicating that it's a poor acid. So if it's a strong base, it's a very weak acid, and vice versa. If we have a very low pKa value for that process, it means that the base itself is very, very weak. Okay. So let's start with electronegativity. So we're going to compare a nitrogen, so NH3, if that was to pick up a proton to acting as a base, we would end up with NH4 plus. And if we were to compare that to an oxygen, so something like water, to give us protonated water molecule, okay, we know that the oxygen is more electronegative than the nitrogen. So if we consider, we're going to do this in pKa value again. So if we think about the NH4 plus, the pKa of that acting as an acid, so losing the proton, okay, the pKa of that is 9.2, okay, and if we think of the water version, to give H2O plus H plus, that has a pKa of minus 1.74. So what that tells us is that for the water example, the equilibrium favours this side. So it prefers to lose that proton acting as an acid. So the conjugate acid, which is the H3O plus, likes to lose its proton. So that means that that one is a weak base. It's not a very good base, so that first process of picking up the proton isn't particularly favourable. We'll see later on that actually protonation of oxygen is quite important in chemistry, but for other reasons that we're not going to go into now. So what it tells us here then is that the nitrogen version is a better base. Now why is it a better base? Well, nitrogen is less electronegative than oxygen, which means that in the oxygen example, the electrons are held much more tightly by the oxygen atom, so they're much less readily available to pick up the proton. So if you imagine there's a lone pair of electrons on this oxygen, and what we're doing is we're using that lone pair of electrons to form a new bond with the hydrogen. Now in the oxygen, the lone pair just isn't very available to do that, whereas a nitrogen, which is less electronegative, has much more availability. The electrons are more likely to form that new bond with the hydrogen. So it's kind of the opposite way around to the acidity, that in this case, to have the more electronegative the atom, okay, the less basic it will be. Now let's consider some inductive effects, shall we? So if we go back to our amine example, so we have our NH4+, we know that that has a pKa of 9.2. And what about if we add a methyl group, which we know is an example of an electron donating group? Well, if we have a single methyl group in our molecule, we actually have a pKa of 10.6. And now remember, if for basicity, if we're talking in pKa value, a higher pKa means that it is a better base. So the higher pKa of the conjugate acid is a better base. So what does this mean? Well, again, just think what we're actually saying is we have NH3, we add a proton, and that gives us our NH4+, or we would have Me, NH2 plus a proton will give us NH3+. We'd have the methyl NH3+. Just draw that out a little better. Okay, so that's what we're talking. So what our pKa value tells us is that the methyl NH2 is a better base than the NH3. And again, let's think about why that would be. Well, one is if we've got an electron donating group that's pushing electrons into the nitrogen, then the lone pair of electrons on the nitrogen that are going to be used to react with the proton, they are more readily available now because there's more electron density there. But we also have an added advantage that the positive charge can be stabilized. Okay, so this is what we would see in the ammonia example of the NH4+, but when we have the methyl group, okay, the positive charge in this case is sitting on the nitrogen because it's used its electrons, but we know that from the work that Professor Osborne did with you that we can, just like when you stabilize a carbocation, we can stabilize that nitrogen positive charge by pushing in electrons from that methyl group. So it has twofold. One is it pushes electrons into the nitrogen, making the electron density on that nitrogen higher and therefore more able to react as a base to pick up the proton. And also once it's picked up the proton, the positive charge that appears on the nitrogen can be stabilized by that donation of electrons into the nitrogen from the methyl group. So if electron donating groups help with basicity by pushing in that electron density and by stabilizing the resulting positive charge, electron withdrawing groups are going to have the opposite effect. If we're going to draw electrons out of the nitrogen, for example, we're going to make that nitrogen less electron dense and therefore less inclined to use the lone pair of electrons to pick up the proton. And again, if we do pick up the proton to form that positive charge on the nitrogen, an electron withdrawing group is not going to help to stabilize that. And we can see that in this example. So we've got another nitrogen that's picked up a proton, okay, and we've got, for this, we have a pKa of 10.7. If we were to take the same nitrogen, okay, same nitrogen, but add on an electron withdrawing group, so something like having a trichloro derivative. What happens here is this trichloro derivative is going to withdraw electrons away from that nitrogen, and we end up in this case with a pKa of 5.5. So you can see, again, remembering that for basicity, the higher the pKa, the better the base is, because what we're saying there is that the conjugate acid, which would be the one that would be losing the proton, is very weak, therefore the pKa value is high. And so if the conjugate acid is weak, the subsequent base from it is actually very strong. So in this case, the pKa of 5.5 shows that the conjugate acid, so the ability for this molecule to lose that proton, is very high. So it would much prefer to just lose that proton and get the electrons back. And so it has a lower pKa. The higher pKa of 10.7 up here shows that this molecule is actually a better base. So the hybridization effects are similar to what we saw with acidity, but as with some of these other ones we'll be looking at, it has the opposite effect that you see with acidity. So again, let's take an example. So we're going to take this molecule here with this amine, in which we have a lone pair of electrons that sit in this orbital, and this is sp3 hybridized. And so what we're looking at here is we're going to add a proton using that lone pair of electrons to give us our charged species, and that we know has a pKa of 10.7. If we look at the example of a sp hybridized nitrogen, where the lone pair of electrons is here, again what we're looking at is forming a positive charge on the nitrogen there. We're picking up that proton, and in this case the pKa for this is -10. So remember what that pKa means is it's the ability of the conjugate acid, the strength of the conjugate acid, which means in this bottom one that a pKa of -10 means that in this system the equilibrium favours the unprotonated substrate of the molecule, and in the top one a pKa of 10.7 means that the equilibrium actually is preferable to be the protonated version. Again, this goes back to the same hybridization effects we saw in the acid, but for the opposite reasons. So in an sp3 hybridized nitrogen, the lone pair of electrons have less S character, so they're not held as tightly to the central nucleus, to the positive charge there. Therefore, they are more available because they're in those more diffuse or further away from the nucleus, more available orbital, and therefore we get protonation. So they make a very good base. Whereas the example at the bottom, the sp hybridized nitrogen, that has much more S-like character, which means the electrons in that sp orbital are held much closer to the nucleus in the center of the atom, and therefore are much less readily available to pick up a proton, and so therefore they don't act as a good base. The final factor that we're going to look at once again is resonance and delocalization, and we'll use our nitrogen example to show that. So remember we have our protonated nitrogen here, and we know that we can lose that proton. So if it was to act as an acid, the pKa of that is 10.7. Now if we compare the same system, so we've got that protonated nitrogen, but this time we introduce a carbonyl, which allows for some resonance. When this is in place, we would end up with, if we act as an acid, we end up with this, and this has a pKa of -1.4. So again, remember what that means is that the conjugate acid, so in this case the conjugate acid are these structures, Okay, it's a measure of how readily they're going to lose that proton. They're going to give up that proton, donate that proton away. And so in the top example, the pK of 10.7 means that that's less likely. In the bottom example, a pK of minus 1.4 means that it's very likely, it's very strong acid. So the H will leave very easily. And the reason that is, again, links with how available is the lone pair of electrons on the original base. So when we're talking about the base, we're talking about the uncharged species here. So how available is the lone pair of electrons? So on the nitrogen, you have this lone pair of electrons that are going to pick up the proton. In this example, we have a lone pair of electrons, whether they're going to pick up a proton. Now, in the version at the top, we have no resonance structures formed. So that lone pair of electrons sits solely with the nitrogen and therefore is available for reacting with the proton, becoming protonated and acting as a base. But at the bottom, we can actually form a resonance structure where we use the lone pair of electrons to form a carbon-nitrogen double bond, break the carbon-oxygen double bond to form this resonance structure where we have a negative charge at the top and we have a positive charge on the nitrogen. So what we can see from this is that that lone pair of electrons is not as available. It is dissociated or delocalized between the nitrogen and the oxygen. So because the electrons aren't available or as available, it's unlikely to act as a very good base. So once again, I've gone through very briefly some of those factors affecting basicity, just picking up one or two examples that show how you should be thinking about the different factors. If you want more detail or if you want to read another version of it, then have a look at the recommended textbook. So that's Essentials of Organic Chemistry for Students of Pharmacy, Medicinal Chemistry and Biological Chemistry by Dewick, and it's on chapter 4. There is areas about acids and bases, and it goes into much more detail. Again, remember that you'll find there's a lot of detail about aromatic systems in some of that chapter, and that's something that we're going to touch on later on in the course when we start looking at aromatic chemistry.